Let's develop some tools for describing steady flow. Steady flow is when the velocity u is no longer equal to 0, but the time derivatives of the system, d by dt, do go to 0. So we're considering when we have a flow that's steady and unchanging, and here are some tools that help us in this sort of system. So u is not equal to 0. That means that we have, if I draw some kind of channel flow here, for example, some flow through a system, we have a flow of fluid going through the system. And we have some different ways that we can try and visualize it. One is to draw vectors showing the velocity u at every point in a domain. And these are very handy. They show us where the flow is. They show us maybe where it's diverging and then coming out and then turning and coming up. And they give us a sense of the full vector field of the flow. And these would be lovely to see. Often we're not able to see this when we just look at a flow that's going by us in a stream or in a continuum fluid system. And so we develop some other tools to help us understand and visualize where these flows are and how the flow works. So we have vectors of flow, which I'll show in blue here. What are some other things that we could put in this flow? The first of these is a streamline, and I'll do that in green. Streamline. And a streamline is a special line. It's a mathematical object, and it's a curve such that u is tangent to the flow at the flow u is tangent to the streamline at every point. So if we define it mathematically in a Cartesian domain, that means that partial x over u is partial y over the v, the y component of the flow, and partial z of the streamline over the z component of the flow. So what that looks like in practice is something like this through our flow. So here's one streamline, and here's another streamline, and I'm drawing so that it's everywhere tangent to the velocity vectors of my flow. You can see that a streamline can really give us a sense of a flow. In fact, if we even had some sort of little like internal circulation here that was closing around, matching appropriately onto the surrounding flow fields, what we'd get is we get streamlines that were closed within. This would be like a small eddy in our system. Nicely illustrated by this streamline. So a streamline is a mathematical object given by this parametric relationship and its derivatives. Now, another tool that we use often in real flows is what is called a streakline. And a streakline is the path followed by dye. So path of dye. So if I come into the flow and I release a blob of dye, put a whole bunch of dye down here, dye. Dye is a passive tracer in the flow, and so it'll flow hopefully following the sense of the flow, and it'll this blob of dye, as it comes along, it'll be at different spots along the way, and we can watch this blob of dye move along the fluid. And in fact, a streak line is the path of dye that's released from a single point continuously. So it makes this streak, this connected streak of flow. And in steady flow, this will follow along the streamlines. In unsteady flow, you have to be careful because the dye shows you where the flow was and where it carried it to, not where the flow necessarily currently is. So the dye is a super powerful visualization technique. We also use smoke, for example, in air or in gases. And this shows you a lot about where the fluid has been, but it doesn't show you the current velocity vectors. And the dye might also, it might have inertia to it. It might have It might have a different diffusion coefficient than the flow. There are lots of reasons the dye might move differently than the flow. You might even, especially with smokes or things like this, you might have radiation coupling effects and opacity effects that cause the smoke to get warmer than the surroundings and buoyantly lift upwards. So those are things you just always have to be a little careful with passive tracers. Are they actually passive? Are they driving the flow in some way? Are they modifying the flow? Are they accurately reflecting the underlying flow? That's a question you have to ask. And the last thing that I want to introduce today is what we'll call a particle path. And so now the idea is that I sprinkle some particles in the flow and I see where do they go to. And I see them sometime later, and then maybe like so, and then maybe like so, and I can watch the particles as they go along. And the particle path, depending on how well I can trace my particles in time, will determine how well I can link up the particles as they go through the flow. Now this is challenging for a variety of reasons. Can you accurately track the particles as they're moving along? Do you get confused by other particles? Can you see where things are going and understand them? Especially for particles released in a flow like this, modern imaging and data analysis techniques are so powerful that you can actually get a very dense sampling of the velocity field and even a 3D sense of the velocity vectors in the system. Now, in steady flow, all three of these, the particle path, the dye streak line over here, and the velocity vectors of the flow, and its streamlines here, all of these coincide in a steady flow. So all coincide in steady flow. But all bets are off in dynamical flow, and you have to be a bit more careful there. Now, I want to introduce one more concept. It is of the stream function. So we've learned about streamlines and streaklines. The stream function is another mathematical concept in the flow. And a stream function is a function. It's a function psi of x and y, such that our velocity is given by derivatives of this. So this is especially useful for two dimensions, and so I'm going to use just a two-dimensional decomposition for the moment. So the x component of u, this is given by the minus d psi dy, partial d psi dy, and the y component of u, this is given by the positive d psi dx. And so more broadly, we can see that we have two different derivatives. The x bit goes in the y direction, and the y bit goes in the x direction. Now, where does this come from? This comes from writing the velocity field of an incompressible fluid, and this is where it's particularly powerful. And the velocity field of an incompressible fluid, one with the divergence of u is equal to 0. Here's our incompressible fluid. The velocity field of our incompressible fluid is nicely represented by this. In particular, we have that if we have that the divergence of u is 0, then we have that dux dx plus duy dy, that's equal to 0. That's our contraction for a two-dimensional velocity field. And as we see for our representation in terms of psi here, that becomes the first one. We get a minus d psi dx dy, and then we get a plus d psi dy dx, and those are the same. We can interchange the x and the y derivatives here, and so this is true for any function psi, and this gives us a lot of power. So for an incompressible flow, the stream function guarantees that the flow itself is incompressible. Lastly, this set of relationships here, these are related to the Cauchy-Riemann conditions tied to the analyticity of a function. So that's a Cauchy-Riemann with two n's. And the Cauchy-Riemann conditions for the analyticity of a function, it looks something like this. It says that we've got a function, and that function takes the form phi of x comma y plus I psi of x comma y. This is our stream function that we were just looking at. And this is called the velocity potential right here. And we'll see that potential flows are a powerful set of tools for understanding simple flows and for solving systems where we have flow in a system and where we have some interesting physics going on. Whereas stream functions, we'll find out, are often useful either for numerical computation or for visualizing the underlying flow.